Engineers called it brilliant for having almost no moving parts. Operators called it a nightmare, so deafening that earplugs and helmets still could not prevent permanent hearing damage. The Argus. Az-014 Pulsejet powered Nazi Germany's V-1 flying bomb, and its 140 decibel roar could be heard for miles, warning targets long before it arrived. Why would history's most disposable engine become its most dangerous, and what made it fundamentally unfixable? The story starts with a design so simple, every moment was a new risk. Inside the Argus, as ZO-14, simplicity hides a violent secret. The engine's heart is an array of thin steel reed valves arranged in a grid at the air intake. At rest, these flaps look almost delicate, but once the cycle begins, they become the only moving parts in the entire machine, shuttering open and slamming shut up to 50 times each second. Fresh air and atomized fuel are drawn in as the valves snap open. An electric spark or a blast of compressed air ignites the mixture, triggering an explosion that instantly spikes the pressure inside the combustion chamber. That pressure surge hammers the reeds closed, sealing the intake and forcing the burning gases to rush out the tailpipe. As the pressure drops, the valves spring open again, and the cycle repeats, over and over, at a relentless pace set by the engine's own resonance. This brutal rhythm, 45 to 50 detonations per second, produces a deep droning buzz. The frequency is not random, it is locked to the length of the engine's steel tube, tuned like a monstrous organ pipe. Each explosion sends a shockwave down the tube, bouncing back and forth, keeping the cycle in motion. The result is a signature sound that is both a warning and a weapon. At full throttle, the Az-014's buzz registers around 50 Hz, a frequency low enough to rattle windows and high enough to drill into the skull. That is why the V-1's approach could be heard from 10 miles away, long before it reached its target. The reed valve grid, while mechanically elegant, is the engine's Achilles heel. Each flap endures hundreds of thousands of flexes per hour, battered by heat, shock, and fuel residue. With no camshafts, turbines, or pistons, the entire process depends on the steel's ability to snap back into place, cycle after cycle. But this simplicity comes at a cost. Every pulse shakes the engine, the airframe, and anything nearby. The same resonance that keeps the engine running also sets up destructive vibrations, an engineering trade-off that would haunt every operator and doom the Az-014 to a reputation as history's most disposable power plant. Preparing a V-1 for launch meant bracing for a mechanical gauntlet. The Argus Az-014 Pulsejet refused to start on its own, so ground crews rolled out a parade of external hardware. First came the Rydell starter, a two-stroke engine bolted to the intake, forced to spin up the cycle with compressed air. Mechanics pumped atomized fuel into the chamber and switched on an electric spark, hoping for immediate ignition. If the Pulsejet coughed to life, it did not ease in. The exhaust shot from cold steel to 800 degrees Celsius in seconds, belching a 20-foot flame straight off the ramp. Anyone standing behind it risked a trip to the infirmary. Burns were common, and the heat could scorch skin through uniforms. Once the engine roared, the real chaos began. The V-1 sat atop a 48-meter launch rail, locked to a catapult powered by steam from decomposed hydrogen peroxide. At the signal, the catapult piston slammed forward, accelerating the missile from 0 to 200 miles per hour in less than a third of a second. That was a 30G jolt, enough to rip loose any tool or limb in the wrong place. Crews worked just feet from the rail, exposed to the full blast of noise and heat. Sound levels hit 140 decibels, well past the pain threshold. Even with earplugs under steel helmets, permanent hearing loss was routine. The launch sequence left no room for error. If the Pulsejet failed to ignite, the V-1 might lurch off the ramp or bounce back, scattering shrapnel and burning fuel. Hydrogen peroxide, the catapult's lifeblood, was volatile and could cause chemical burns on contact. Every launch was a calculated gamble, one that sometimes ended with more casualties on the ground than in the air. The only upside, if you can call it that, was speed. The entire ordeal, from startup to airborne, lasted less than a minute. But for the crews, those 60 seconds felt like an eternity spent dodging fire, noise, and flying debris. Simplicity in this case came with a heavy price tag, paid in hearing, skin, and nerves. Measured by any engineering standard, the Argus A014 Pulsejet is a study in catastrophic underperformance. Thrust output peaked at just 750 pounds of thrust, a figure that might sound respectable until you factor in the fuel consumption. 1 gallon burned every 2.5 seconds. That is 24 gallons per minute, all to keep a 400 miles per hour cruise missile in the air, barely. The engine's thermal efficiency clocked in at 2.7%, meaning more than 97% of the fuel's energy was wasted as heat, vibration, and the infamous mechanical shriek. For every hour of operation, the A014 converted enough gasoline into noise and exhaust to power a small fleet of trucks, but delivered the mechanical output of a single family car. This inefficiency was not just a theoretical problem. The service life of the engine, even under ideal conditions, rarely exceeded 30 to 60 minutes. The reed valves, battered by relentless pressure pulses, typically failed after 20 to 30 minutes of operation. Once a valve cracked or lost its spring, combustion became erratic, thrust dropped, and the engine either flamed out or tore itself apart. The combustion chamber, made of thin, mild steel, cycled from ambient temperature to 800 degrees Celsius in seconds, then back again after shutdown, causing welds to crack and metal to fatigue. Mounting bolts, subjected to 4G vibration peaks at the engine's 50 Hz resonance, worked loose mid-flight, sometimes detaching the engine or even the entire tail section. Field reports document tail separation in 30% of V-1 missiles, a figure that would horrify any modern airworthiness inspector. Every design compromise fed back into the same cycle of destruction. The resonance that kept the Pulsejet running also shook the airframe to pieces. Instruments failed, control surfaces vibrated loose, and after just 1 hour, the entire missile was often structurally unsound. The A014 did not just fail gracefully, it failed spectacularly, and on a schedule you could set your watch by. The numbers do not lie. This was an engine designed not to last, but to run just long enough to reach a target, or to disintegrate trying. Cheapness was the only metric that mattered to the designers of the Argus A014. Each engine rolled out of underground factories for just 350 Reichsmarks, a fraction of the cost of a single fighter plane. But the low price tag came at a human cost that never appeared in the ledgers. Production lines ran deep beneath the Harz Mountains, staffed by forced laborers from Mittelbau-Dora and other camps. For many, life expectancy was measured in weeks. Shifts stretched for 16 hours, food was scarce, and safety was a rumor. Survivors later recalled sabotage as their only defense, weakening welds, misaligning valves, anything to slow the relentless pace. Records estimate over 20,000 laborers died building V-weapons, more than twice the number killed by the V-1 attacks themselves. Hannah Reich, one of Germany's most celebrated aviators, climbed into the manned version of the V-1 and found herself at the mercy of the Pulsejet's violence. The engine's resonance blurred her vision, shook her organs, and left her with a single, damning verdict. She said it was a metal torture device, not an aircraft. She refused a second flight. Her report helped end the Reichenberg program. Unmanned Phi-1 flying bombs continued to fly, powered by engines that shook themselves and their makers to pieces. The same flaws haunt modern tinkerers. Hobbyists around the world have tried to tame the Pulsejet, lured by its simplicity and the promise of raw power. In the United Kingdom, a builder named Pulsejet Pete strapped a homemade engine to a go-kart and managed 85 miles per hour before the reed valves failed and the chassis nearly rattled apart. Others have built Pulsejet dragsters or mounted engines on bikes only to find the same pattern: catastrophic vibration, deafening noise, and a lifespan measured in minutes. No matter the era or the materials, the Argus A014's legacy is inescapable, an engine that punishes anyone who tries to make it last. The only thing it ever produced reliably was regret. Today, engineers still study the Argus A014, not to replicate its simplicity, but to avoid its catastrophic mistakes. As technology accelerates, the lesson endures. Cutting corners for speed or cost can cost much more in the end. Simplicity isn't always progress. Thanks for watching.